Working? Okay. All right. Thanks yet again for coming. Keeps amazing me that you still keep coming. So we are finally almost ready to begin exploring physics of the early universe, actually. We have the basic tool set, and we're not going to do very much more in terms of, pedagogical constructing this tool set, because really the most important thing for us from the cosmology side is this Hubble expansion rate and the continuity equations for the various forms of energy density in this universe. And we know, in addition to these conservation equations, we know another important property, which is that we know that the energy of a photon, the energy that it had at some redshift z, is related by a factor 1 plus z to the energy of the photon at the redshift we see today, which is 0. And also for a free streaming distribution of photons that are not scattering with anything and have the observed black body distribution, this black body distribution has a temperature, and you can easily convince yourself, just using this, that the effective temperature parameter of this distribution function of the photons at redshift z would be given by 1 plus z times the temperature of the photons that we measure today. Okay, so typical energy per particles that are colliding is increasing as we increase z and scroll back time. Okay, excuse me. So while I set the power up, any questions from before? Okay. Okay, so when the energy scale of particle collisions increases, the interaction rates that describe these collisions also change. And this is what I want to discuss next. And this has to do with the topic that's called thermodynamics. In expanding universe. And we will only just very barely touch it, even though I would love to show you some of the basic properties of this physics. We'll just touch it. All right. So we want to calculate the rate at which certain particle collisions happen as we scroll back time on our average homogeneous and isotropic universe. And we looked at one such reaction. One such reaction is Compton scattering. So a photon scatters on an electron, like this. And we calculated the rate that this reaction takes place. So this reaction takes place at the rate that a photon traveling in the universe undergoes collisions with ambient electrons. This is the rate that I mean here, is given by the target densities of these free electrons times c times the cross-section for the interaction. Okay? And I just drew the diagram. So in the limit that the photon energy in the initial state, okay, so I'll characterize it by a temperature of the initial state, is smaller by a lot than the mass of the electron, then the energy flowing in this propagator, the Q flowing in this propagator, is much below the mass of the particle that we're exchanging. And then we have a typical interaction. So then the cross-section relevant in this limit is that sigma is of order alpha squared over me squared, up to another one coefficient. Okay? On the other hand, I could consider the situation if I now keep on scrolling backwards time and making the redshift larger and larger and larger, then our good old CMB photons would have exhibit a huge temperature as large as I want to give them, as large as I'm willing to scroll back time. So at some point or another, I'm going to hit a time where this temperature of the photons is larger than the electron mass. When this happens, the typical Q squared flowing in this propagator is larger than me squared. And then what I need to take is the energy that's going in here. And then, in this case, my cross-section has to scale parametrically like alpha squared over t squared, where t is the typical energy flowing in this propagator. Okay, because cross-section has units of centimeters squared or 1 over energy squared in natural units. So in these two situations, I can write my reaction rates. Okay, so gamma, which is NEC sigma. In this case, my reaction rate, because the electron number density scales like redshift cubed, it's just a number density, okay? And redshift is the same as temperature, then my reaction rates here scale as alpha squared t cubed over ME squared. Now, we don't have to go through all of these considerations of the electron number density scaling like Z cube. Actually, dimensional analysis is enough because we are done with the massive particles in this object or just coming in as an effective interaction. The only other scale of dimensions of energy or 1 over centimeter are temperature in this problem. And a rate is in units of 1 over second or units of energy. So it has to be t cubed here. You don't have to work too hard with order 1 numbers. In this limit, however, the interaction rate has to go like alpha squared t from the same considerations. And I can plot as a function of temperature, universe temperatures, that is the typical temperatures of the photon bath. I can plot the rate of this interaction. I'll do it far away, otherwise I'll have to erase it very shortly. Okay, so as a function of temperature or redshift, just proportional to each other, let's make this T naught or Z equals 0. I can plot the rate, gamma, and at early time for this QED interaction, at early time, this rate shoots up with gamma QED going like T cubed, okay? And at some late time, when the temperature hits the mass of the electron, let's make this ME, this rate better break and soften up and continue to go like a single power of T, okay? With some alpha squared in front. Okay, so this is QED. And I just mentioned a confusing statement in the very last few seconds of my previous talk, and I said that this range is actually not correct. And we will shortly see how to correct it, but the qualitative behavior is correct. Okay, so you don't have to worry about right now, but this is the reason that I put a dashed line here. I will correct this dashed line. It's the reason that it needs to be corrected is that these parametric scaling arguments are broken, in fact, by a very funky behavior of the free electron density. So that's QED. We can work out another example. We can work out, for instance, weak interactions, neutrino scattering. So let's consider a neutrino scattering, for instance, again on an electron, if you want, okay? And giving me here a W going to whatever you want. So let's take it back to my neutrino. And various other weak interactions that I could plot. Now here I have the W boson propagator, and the mass of the electron is 0.5 MeV. The W is more massive than this. So the interaction rate for the neutrinos, this was QED, for the neutrinos would be roughly n baryon, because we have these weak interactions happening with everybody around. C times the cross-section. And now my cross-section for this interaction, as long as the temperature, typical energy of the particles in the initial state are below the W mass, okay, so W mass is about 79 GeV this time. We've scrolled time far backwards, but as long as the temperature is smaller than about 80 GeV, This is again an effective interaction, and it scales like G Fermi squared. So G Fermi is roughly alpha over mw squared. I have a single propagator here, and I need to square it, so I'll get the alpha squared over mw squared. And so I have to have a t squared in here, okay? Just to remind you. So I can write this number. This effective interaction is about 10 to the minus 5 GeV to the minus 2, a constant of the standard model at low energies. Okay, so this is what happens at low energy, and therefore, when the temperature of the participating particle, say the neutrino here, is much, much smaller than mw, this interaction rate, this is my cross-section, and the interaction rate will have to scale like t to the 5, because I have another power of density. And also because gf squared has dimensions of 1 over mass to the 4. Okay, and interaction rates have powers of mass. So this will scale like gf squared t to the 5. When the temperature is so high that it's actually higher than the W mass, then a similar thing to what happened to QED will happen to us. And the interaction rate will have to scale, roughly speaking, like alpha squared t. It's not precisely alpha, it's just G, it's not E, but other than that, it's the same parametric scaling. No need to introduce more notation. Okay, so this is when the energy in the propagator is higher than the W mass. So I can draw a similar diagram for neutrinos, similar to what I did here. But I have to extend this axis a lot. Okay, so I have to go to the scale of mw. And at around the scale of mw, these neutrino interactions are in fact comparable. So this was alpha squared t. And in fact, the neutrino interactions are comparable to the QED interactions, and they scale like t. Okay, and I can extend it up. However, around at MW, we have to take into account the effective theory, and this neutrino interaction is going to fall like a rock. It's going to fall down like t to the 5. Yes? I'm sorry? This? No, there is no GF anymore. So GF is defined as some funny power of, so this GF, just to remind you, I forget my square root 2's, but it is G squared over MW squared. And you can think about it essentially as the coefficient of this diagram. So the effective weak interaction, the Fermi theory, is a 4 fermion theory suppressed by some non-renormalizable coefficient. So it's a dimension 6 operator. And this is the suppression scale. Okay? And it goes like 1 over MW squared because I have a boson propagator in here. Okay? So this is the way this GF enters in the Lagrangian. Right? So it has dimension of 1 over mass squared. And so, but it's really coming from the effective Lagrangian coming from propagators just like this, tree-level diagrams like this, with a single gauge boson propagator with 0 Q squared coming in, or Q squared much smaller than MW. But when I'm looking at very high energy, the Q squared is much, much higher than MW. So there is no room for an MW suppression. MW doesn't exist at this energy. It's replaced by T squared. When it's replaced by T squared, it kills T to the 4 in here. So if you want, my G squared comes with a factor of MW to the 4 over T to the 4 at high energy. Okay. You will have a bunch of other diagrams suppressed by other scales. So I'm meaning this as an example, 2 examples that exist in the standard model, but whatever other interactions that you give me, I can calculate, how these interactions scales at low and high energy. So,
I can modify that.
oh yeah, you can modify that. However, you better not modify that by a lot around the W mass, because that place we've burned down to the ground, right, with the LEP and the LHC, more or less. Okay? So if you want to modify this physics at the TeV, be my guest. And it's, in fact, a very good point that at energies much above the W mass, I've continued these curves, but I'm continuing these curves extrapolating the standard model. And I should warn you that we have no direct observations, I would say, or direct observational information on processes that are happening at such high temperatures. So I am extrapolating, and there could be other interactions, or these interactions could change at very high energies if the standard model is broken. So when I do this, when I go far back, I'm assuming standard model. We are not going to need it. I just want to give you the qualitative picture. And if you have more physics, more new physics, et cetera, or whatever new physics that you want, you can generalize this exercise. All right? But I am indeed extrapolating here far above MW. But up to about MW or up to a few TeV, we know what we're doing directly. So where was I? Yes. So I wanted to add on top of here the Hubble expansion rate. Okay, and you have the equation for the Hubble expansion rate. And I just remind you, without computing anything now, so this Hubble expansion rate today is essentially constant with temperature because it's dark energy dominated, we think. Okay? But then very quickly, it begins to rise. I'll give it its own color. It's constant initially. Then it begins to rise, and you know this slope. So this slope is temperature to the 3/2, okay? Because it's the square root of z to the cubed. Then it goes on like this for a bit until a special redshift that was mentioned today, which is the redshift z equality. From that point on, radiation takes over, and this expansion becomes harder. Okay? And the Hubble rate in the radiation-dominated epoch scales like t squared. Okay, we will write the exact expression in a bit. But it's easy, you can do it yourselves. So it scales like t squared, which means two things. If I'm allowed to continue my bold extrapolation here, it means two things. The first thing it means is that above some redshift, both of these interactions, this is what I call the QED and the neutrino, the weak interactions, above some redshift, they inevitably are going to take over the Hubble expansion rate because they have a steeper power law in temperature. Okay? So somewhere in here, gamma neutrino will be larger, inevitably much larger than the Hubble rate. And somewhere in here, gamma QED is much, much larger than the Hubble rate, okay, after a certain redshift. And it's also true that at lower redshift from these special points, then the QED scattering rate and the weak interaction scattering rate will drop below the Hubble rate. Let's make this Hubble rate really thick. Oh, I have a new eraser. Okay, so this is an important curve. Good. So here the QED rate, let me go to neutrinos, more robust. Neutrinos will be much, much smaller than Hubble. That's the first thing, okay? And this epoch, this time in the evolution of the universe where the weak interactions are much, much faster than Hubble means that these weak interactions, processes going through weak interactions occur very fast per unit universe dynamical time, and they have a chance to reach thermodynamic equilibrium, okay, which I'll define in just 1 minute. So in here, interaction rates reach thermodynamical equilibrium. Same happens for the QED interactions. At low energies that drop out of equilibrium, they so-called freeze out, and I'll show you what it says. So that's one thing. The second thing is that at sufficiently high temperatures, if we are allowed to extrapolate that far, in fact, all of the standard model interactions, being a renormalizable theory, the standard model, it means that because I have no scale, when the temperature is larger than any mass scale in the standard model, then being a renormalizable theory, all reactions of the standard model at high enough temperature will scale like the linear power of temperature, just on dimensional grounds. But Hubble expansion rate is dominated by what is to us a non-renormalizable theory, yes? So this Hubble expansion rate, what is it? It is 8 pi g over 3 rho. So in this epoch, it is radiation dominated. It's enough for me to take the radiation energy density, square root, just the equation I wrote before. Well, G is 1 over m Planck squared in natural units. Gravity is an effective theory, as you all know. It's oppressed by a large mass, m Planck, which is about 10 to the 19 GeV. Being an effective theory, it shoots up, this dynamic time shoots up like a strong power of t. It actually goes like square root of rho r, so it goes like t squared over m Planck. And that's another view of our t squared. Okay? Therefore, it has to take over, at some point, our normalizable standard model interactions. So at some point, our interactions are again out of equilibrium with the Hubble expansion rate. And I simply don't have time to discuss the wild speculations that we have about what's going on in here. The only thing that I have is I can estimate this temperature when the standard model interaction are frozen out. So this is very easy for us to do. So this point is when standard model rates, which scale like alpha squared t, are roughly the same order as the Hubble expansion rate, which is t squared over m Planck. Okay, let's call this temperature t tilde, and we can solve for it. So our t tilde, what's going on? Our t tilde is alpha squared m Planck. This is 10 to the minus 4, so it's about 10 to the 15 GeV. So if you allow me this wild extrapolation at high enough redshifts and temperature, all standard model interactions are slower than expansion. Now, why do I care when interaction is really slower or faster than expansion? There is a very simple way to understand this. So you saw two examples of interaction rates that scale like some power law in temperature with some big power n. Okay, so let me, for simplicity, consider radiation domination time, though it's very easy to generalize. So with some power n that is larger than 2. Okay, so QED below the electron mass is 1. It scales like t cubed, n equals 3. And weak interactions have t to the 5. Now, in radiation domination, the Hubble rate scales like t squared. Okay? And we can do a very simple calculation of asking, take these interactions, for example. If we start to look, so up here it's clear to us that many, many interactions are taking place over a dynamical time. Yeah, it's very clear. But we can ask the question quantitatively, how many, in total, how many interactions does a neutrino experience from this universe time, this redshift? This is not ME, I hope it's not confusing. This ME was for that break, okay? So but it's not far, actually. So how many interactions does a neutrino exhibit from this point in time until today? In this entire interval, from redshift of 0 to redshift of order 10 to the 10, which is the answer for this freeze-out temperature, okay? So we can ask, how many interaction does the particle have from, let's call this special temperature T freeze out until today, when T freeze out is defined as the temperature when the Hubble expansion rate equals the interaction rate. Okay? We don't have to solve any Boltzmann equations or complicated stuff for that. So let us just compute this number of interactions. Okay, so this number of interactions will be equal to the time integral from that freeze-out time until today, multiplied by the rate, the number of interactions per unit time that the particle has as a function of time. Time is a very poor label for integrals like this. Redshift or temperatures are much better. So let me convert this integral to redshift, okay? Okay, so we know that dt is a dot is dA over a dot, okay? And we know that this is equal to dA over a Hubble, because the Hubble rate is just a dot times a, okay? And now redshift being defined as a equals 1 over 1 plus redshift, dA over a is very easy, so this is minus dz over 1 plus z times the Hubble of z. So this is just, I wrote dt in a fancy way, so, or convenient way. So I can just convert this integral to integral of redshift. So this is an integral now from 0 until the time of freeze out times dz gamma of z 1 plus z h of z. And now it works that I decided to look in radiation domination where the Hubble rate is a power law, but the same thing would work also around transition when the power law changes for the Hubble law and the interaction. The essence is the following. So in radiation domination, I can drop the 1. Again, this is a simplification you don't really need to make, okay? But I can drop the 1, and I can write this as gamma of z freeze out over the Hubble of z freeze out times integral dz. And here I have z over z freeze out to the n. And I have z and z over freeze out squared. So I might as well convert this integral, because I have dz over z, change the variable of integration to, say, chi, defined to be z over z freeze out. And I can change this. I can write this integral as gamma over Hubble at freeze out times integral from 0 to 1 d chi over chi, chi to the n minus 2. So I have chi to the n minus 3. I can't. I'm making my life easy, and it's unneeded. You should verify it later. So, and it's just that I'm never going to really need the 0. That's the important part. But I can't. You can keep it and check. Okay? Sorry? I'm missing a factor of z freeze out? Really? Because I have dz over z, and each of these I factored out. So I think I should be fine. But I'm having trouble doing this integral at z freeze out. So what I have here, 1 over n minus 2, and that's it. And there is some coefficient here. No, there is no. So 1 over z minus. Good. Excellent. So that's exactly my point. So I've assumed when I started that my interaction rate is such that n is larger than 2. Okay? So this object here is smaller than is going to be of order unity for gamma exactly 2, but for QED and neutrino interactions, for the QED example, this number here is just 1. For the neutrino interaction, this number here is 5 minus 2, so it's smaller than 1. And the definition of the freeze-out redshift is that the gamma over h at freeze-out is 1. And we've just calculated the total number of collisions that your particle is going to have from, say, this point until today. And this number is smaller than 1 with our QED and weak interactions, okay? So this is the meaning of this freeze-out. This is the significance. Sure, your particles, some of your particles will exhibit some more interactions, but on average, each particle is going to exhibit less than 1 interaction on the entire duration from this point until today, okay? So in this sense, interaction is not important. It's another view of what's happening. So another way to say it is that the dynamical time, the Hubble time, here is much, much shorter than the interaction time. But we've just looked at the integrated version of the same thing. So this is what freeze-out means. No more interactions until today. And exactly analogous thing happened here. So if I would do the same integral but going upwards from this redshift, I would find that from this point until as far as you are brave enough to go, the standard model particles will have no more interactions between themselves. The dynamical time is so fast that it wins over it. Okay, so no more interactions in here. Never have been any interactions until here. Many, many interactions that are fast occurring in here. And again, no more interactions going down in here. But in these regions, there are many interactions. And so we can discuss what happens here in the range of fast interactions compared to dynamical time. Okay, so I would like to erase this. So I've been trained by my students to say this. I would like to erase that. I've not been successfully trained to actually wait for them to object. But you should object if you're writing or anything and you want it to be kept. Okay, so I'll erase this simple calculation. We understand the meaning of freeze-out. And of course, you could compute, for instance, how many interactions you would have if you would go from Z freeze-out by a factor of few up into this epoch, and you would find a big number. There would have been many, many interactions at this time. So what happens in this epoch of equilibrium when gamma is much, much larger than the Hubble rate, okay? So, and what do I mean? For QED, I mean this bulk of redshift here, and for the weak interactions, it's this range of redshift. So when the interactions are fast, the distribution functions of the particles in this plasma are going to reach a maximum entropy solution, okay? Basically, the expansion, the dynamical time, expansion is so slow that it is adiabatic, it's very slow, and we can basically freeze out time, look at the slicing time, and this slicing time, nothing changes for long enough duration that the distribution function reach a local thermal equilibrium. It's not an exact thermal equilibrium, because there is still always a slow expansion, okay? But it's very, very near to a thermal equilibrium if interactions are very fast in this slice of time, as they are for QED in the weak interactions. And then we'll reach maximum entropy distribution functions. So the distribution function for a particle is defined as follows. So if you look at a chunk of redshift, d3x, d3p, then the number of particles in this phase space chunk is given by the phase space volume multiplied by the distribution function, and I will multiply, by definition, I will give a multiplicative factor of the number of degrees of freedom. So if I sum, say, photon helicities, so number of degrees of freedom over 2 pi cubed, just to work with the natural phase space, okay? And this distribution function, the maximum entropy ones, are just the Bose-Einstein ones, or Fermi-Dirac distribution. So there are 1 over E to the energy minus the chemical potential over T, plus or minus 1 for bosons or fermions. Okay? And once we are in a maximum entropy distribution, we can compute immediately all thermodynamic quantities. So for example, the energy of this gas of particles is G over 2 pi cubed. I just need the energy density. I just need to integrate over the phase space times the energy of the particle times F of E. I'm assuming isotropicity and homogeneity, so distribution functions are only function of energy for a particle. And the pressure is similar. We could easily derive it if we had time. And we can also write number densities, which are even simpler. F of E. So there is a famous consequence of this maximum entropy distribution functions that characterizes this epoch of equilibrium, which is the statement of entropy conservation. So you've heard it in this course. Just to remind you what it says, I will not derive it. But in fact, when we have assumed that the distribution function attained maximum entropy form, then entropy is already conserved. We've just assumed it. It follows from this form of energy momentum, of the energy and momentum and number densities. And also it follows under the assumptions that the chemical potentials here, which is the energy that you obtain by removing or adding a particle to the plasma, yes? These chemical potentials should also be thought as functions of temperature alone. Okay, so in the maximum entropy, all of these distribution functions should be thought of as slow varying functions of temperature or redshift alone. And then entropy is guaranteed to be conserved. I just say it as an aside. So entropy density, defined as rho plus T minus mu n over T is conserved in the sense that the differential of A cubed S is 0, and it is conserved separately for each collection of particle species in the fluid. It's a nice exercise to calculate and show that this is true once you have assumed this form of the distribution functions. Okay, it just follows from the form of F. But I let you work it out yourselves. As a consequence of this identity for the maximum entropy distribution functions, it follows that, in fact, the temperature of the photons in this gas don't just simply scale as redshift anymore, because they're subject to constraint, to this constraint of maximum entropy. So I can write the entropy of this gas. And for this, let me first write for you the results for this rho p and n, or some of them at least, in the limits of very relativistic particles or highly non-relativistic particles. So for instance, the energy density of this kind of particles has two limits. So in the limits that the temperature is much, much larger than the mass of the particle, this energy density is pi squared over 30 g t to the 4. We did it already for the photons, where g was 2. And when t is much, much smaller than m, then it is g times mt over 2 pi, 3/2 e to the minus m minus mu over t. I've ignored the correction from a chemical potential here, assuming that it is small, but it is easy to compute the correction from a chemical potential in the relativistic case. It will not matter to us ever, but in the non-relativistic case, this chemical potential will matter to us, in fact. Good, and I could write the same expression for pressure. The pressure for the non-relativistic case is proportional to the velocity times, velocity squares times the energy density, so it is suppressed. The pressure is suppressed for the non-relativistic case. We can ignore it. It's back to our gas of galaxies. And the pressure for the relativistic case is simply 1/3 of the energy density. Okay, so no need to write it. And I could write also an expression for n, but I'm not going to bother to do it. And ignoring for a moment chemical potentials, the entropy in this case of this plasma will be the sum of the particles interacting with the plasma. So I should have here that there is a constant. Let's call it Ci, if this was Gi. And this Ci is 1 for a boson, and it's 7/8 for a fermion. And now I can finally write what I want. So the total entropy is the sum of the entropies of this plasma. And I can write it, I can omit from the sum of the entropies the contributions of all the species that are in thermal equilibrium but are massive, highly non-relativistic, because these species are going to be Boltzmann suppressed by a big exponential factor. So entropy will be dominated by relativistic species, neutrinos, photons at high enough energy, electrons and positrons. Okay? So it will be the sum. So it's all radiation. So I have this plus 1/3 of this, which I believe is 2/45 pi squared, T to the 4. Let us choose as a label the photon temperature times the sum on I, Gi, Ci, Ti over T, of course, cubed. Okay, because I have 1/T in here. So this is the conserved quantity. And this object here is known as GS, and it's in principle a function of temperature. The reason that it is a function of temperature is because as I vary the temperature, some species of particles eventually become non-relativistic. So as I scan, as I look at this plasma below the electron-positron mass, the only relativistic particles I would have are photons and neutrinos if they are still coupled to the plasma. Okay? But above the electron-positron mass, I have to add the electron and positron contribution to this sum. So GS is a counter. It sums up all the particles that are in thermal contact and that are relativistic. Particles that are not relativistic are Boltzmann suppressed and are dropped out. Of course, you can compute the full expression from here. Okay, but this is a good proxy. And now the statement that S is conserved here means that the differential of A cubed times T cubed times GS of T is the thing that is conserved. Whereas when we ignore this point of entropy conservation, it would be A cubed T is conserved, and therefore T would scale like 1/A. So T scales almost like 1/A, but not exactly. There is a counter, another one number that makes these variations a little different. Okay, so that's an aside. And now I want to compute things, because I really promise that I'll do some new things here. And I really want to do it. So the first thing we're going to use these toolboxes to calculate is recombination. So the last scattering surface. And then I have time to do to explain to you the latest CMB Planck constraints on dark matter annihilation, just using these tools. So that's my plan. So the first thing we will do, we will calculate recombination approximately in the equilibrium approximation, okay, which Javier already mentioned today. We'll just derive it very quickly from what we did. So the way we'll do it, what do I mean by recombination? What I mean by recombination is, as I scroll time backwards, temperatures go larger and larger. Eventually, at very high temperatures, the photons of the CMB are so energetic that whatever neutral hydrogen would be floating around would be ionized. So at these very, very high temperatures, all hydrogen has to be ionized. It's basically a plasma of electrons and protons. Okay? So this is obvious. When you scroll back time, photons so energetic, then this will happen. So at very high redshift, everything is ionized. And also, we're in this epoch of equilibrium for QED, deep inside it. We don't care about subtleties here. Okay, so we have equilibrium distribution functions for protons, electrons, etc. They're interacting fast. And we know the initial conditions that they are all ionized. And what we want to calculate is this cosmic instant where suddenly, we'll see it suddenly, they recombine. Protons and electrons recombine to form hydrogen. So let's just do it very, very quickly. Well, at high temperature, so T larger than, say, 1 electron volt, as it turns out, we have a plasma of mostly E minus P and some very little trace of hydrogen. I'm ignoring helium for this calculation, okay? And we have a tiny bit of hydrogen. You'll see in a minute how tiny, okay? And the density, all of these particles, at temperature larger than EV but smaller than ME, okay? All of these particles are highly non-relativistic. So because the interactions are fast, they are in equilibrium, and they have this energy density. Of course, here what I wrote, you should have corrected me, is energy density, so it misses a factor of m. Number density is the same expression without m, and now I will need it. Okay, so this expression, I write it as m times g, which is m times the number density. Okay, so this is the number density of the particle in its units of energy cubed as it should. So the number density, for instance, of electrons is g electron MET over 2 pi e to the minus t minus mu electron me minus 2 electron over t. And I can write the same expression for the protons, and I can write the same expression for instance, the hydrogen. So there is some trace hydrogen. You'll see how small in a second. So, and this is G hydrogen times M P T over 2 pi hydrogen over T, okay? And because the interactions are very fast, these chemical potentials are related by the reactions of recombination and ionization of hydrogen. So interactions are fast. And so you have these reactions, E minus and protons meet and go into hydrogen and a photon. So this is recombination, and this is ionization. When these reactions are fast, the chemical potentials are equal. So the sum of chemical potentials is additively conserved. And chemical potentials of photons is 0, okay? Because there are reactions like this. That take net 0 chemical potential to photons. So photon number is not conserved, as well as reactions like this that change the number of photons, so photons have no chemical potentials. Okay, so I have this equality. Because of this equality, I can replace this mu-h by the sum of chemical potentials of E and P. Okay, so it's that simple. So what I have here in the exponent is E minus mh minus mu P minus mu E over T. And it's convenient then to use the binding energy of hydrogen, which is defined as E hydrogen is MP plus ME minus M hydrogen, and that's your famous 13.6 electron volt, the ionization energy of hydrogen. So I can also replace this MH by MP plus ME minus EH, okay? So I have an expression for E, similar expression for P, and an expression for H, and the exponential parts in these expressions are related. And if I take products of these expressions, I'm going to get the same exponential up to the binding energy. Yes. Thanks. Raise this. Okay, so I can combine these expressions. I can take the product, Ne, Np, over Nh. and just see what I get. So I get GE, GP over GH, MET over 2 pi to the 3/2. Now I can cancel, outside of exponential, I can cancel the ratio between proton mass and hydrogen mass. I've already used just the proton mass in here for hydrogen. So this factor drops out in the product. And what remains is just the exponential. So for the electron and proton exponential, I have minus ME plus MP, which will just cancel that. And I have minus mu P minus mu E, which would just cancel that. But here I have an E to the EH over T. So what I have is an E to the minus binding energy over T. And now, note that the sum of protons and the sum, so ionized protons and neutral protons have to sum up to the total baryon density. So NP plus NH is just the baryon density. And it's also convenient to note that the baryon density to relate it by some factor eta to the photon density. Okay? And this eta is very well measured from, in particular, BBN, and it's about 6.1 times 10 to the minus 10. This is the famous statement that there is a huge amount of photons per baryon in this universe. Okay? So when I do these replacements, it's also convenient to define XP as the fractional ionization. So this will be NP over N baryon. So of all the baryons, which I'm assuming that are all protons here, how many are ionized? Okay, so this is the dimensionless number XP. It can go from 0 to 1 for us. And this is also equal to NE over NB because the plasma is neutral. Okay, so this equation I can now rewrite in terms of X. And it says XP squared over 1 minus XP is everything on the right. So I have GE, GP over GH. Over T. And I have here 1 eta and gamma. So all of this is multiplied by 1 over eta and by 1 over n gamma. So now I have no choice. I need to tell you the number density of photons. So this n gamma is G times zeta of 3 over pi squared T cubed for relativistic particles. So I can plug it in here. And I have 2 zeta of 3 pi squared. And this T goes down. Now I have a dimensionless equation that we can immediately analyze. Okay? This equation appeared today in Javier's talk, and it's called the Saha equation. And it's the equilibrium estimate of the fraction of ionized protons in the plasma. Okay? And as Javier said, equilibrium will be broken at some point, but equilibrium is good enough for us to get a rough understanding of what's going on. And everything here, besides from mu over t and eta, right, and the exponential, all the rest are order 1 numbers. We can write what these order 1 numbers are. Okay, so just to accompany this equation, well, GE, we have just electrons, we don't have positons here. So GE is just the spin degrees of freedom. GP is the same. And hydrogen, neutral hydrogen, has it's a proton and an electron, so they can align in a singlet with opposite spins or in a triplet with a vector configuration, spin 1 total spin configuration, so it has 4 degrees of freedom. And zeta of 3 for you is around 1.2, just a number. So let's analyze how this equation behaves. Questions so far? Okay. So this is an extremely important equation. It's an important equation because photons low energy photons don't scatter off or scatter highly inefficiently off protons, and they don't scatter off neutral hydrogen at low energy. They only scatter off free electrons. Okay? And this XP, shortly I will also call it XE, is just the fraction out of the total baryon density that we know of the electrons that are free and available to scatter our photons. Okay? So the amount of available electrons is crucial to calculate the mean free path or the scattering rate of photons in this universe. Okay? So as a function of redshift, we can now explore this equation and see how it behaves. And so let's call it this XE up here. It's the same as my XP. So at some very early redshift, temperature is very high, smaller than ME, but that's fine. Okay? So this is some polynomial of the temperature. The exponential is close to 1 because I'm going to temperature that is larger than the binding energy of hydrogen. So let's go to some T larger than EH, but much, much smaller than ME. And down here, I have order 1 expressions, and down here, I have a number that is 10 to the minus 10. Okay? So all of this expression is of order 10 to the 10. And remember that the dynamical range of my XP, so my XP is in the range 0 to 1, because it's a fraction. It's a fraction of free electrons out of the total. Okay? So that's its dynamical range. And now it wants to give us a very, very large number at high temperature because of this eta. This eta is 10 to the 10. Okay? So the only way for this object to give us a very large number is for XP to be very, very close to 1. And so the solution at very high temperature is around 1. And it's not going to do anything interesting before that. Now I scroll temperature down, and eventually at some point, the temperature will begin to be significantly smaller than the binding energy of hydrogen, and then everything will recombine because this exponential is going to make the whole thing on the right very, very small, exponentially small as I go down in temperature. And so this object wants to now give a very small number, and the only way for it to do it is to make XP exponentially small. Okay? So when temperature goes down, our XP has to go down exponentially. And if psi equilibrium had its way, then it would just continue to go down exponentially to 0 when the temperature cools. But we don't have to go that far. Okay? So what is the temperature where this is happening? Temperature this is happening can be estimated by taking a log of the right-hand side and asking when, at what temperature, all the right-hand side is of order unity, or the log is of order 0. Okay? And so the log is of order 0 when EH over T, so I have minus EH over T plus log of 1 over eta is of order 0, ignoring all the order 1 numbers and polynomial corrections, okay? Which means the solution of this is that the temperature of recombination is roughly the binding energy of hydrogen, as you would expect, divided by log of 1 over eta, which is roughly, so this is roughly 30. So we found cosmic recombination. Let's prove that we found cosmic recombination. So this electron density falls down very, very small. In fact, as I said, psi equilibrium would say that it falls down indefinitely small, but equilibrium is broken down at some point because interactions becomes slow because there are no more free electrons to scatter on. So this actually freezes out. And it freezes out at a number of order 10 to the minus 4, which will not be very relevant for us right now, but shortly will. And then it stays close to 10 to the minus 4 for a long time. Now the redshift where we reach this temperature, so the correct number here is about 0.2 electron volt. And we can just compute it very easily. So the redshift of recombination from this calculation is that Z recombination is T recombination divided by the photon temperature today. Okay? The photon temperature today is about 2 times 10 to the minus 4 electron volt. We already did it. So this recombination is of order 1,000. And the more precise number is 1,100. Okay, we just got it as a function of eta and the binding energy of hydrogen. So this is this time. Of order 1,100. Now the ionization flow is going to, this ionization flow is going to continue like this until at a much later time, some new event happens, which we call Z-ionization, and this ionization flow shoots up. So because you remember that I told you at the first lecture, I think, we already estimated the mean free path for photons in the universe, and in this estimated, I assumed that all of the electrons in the universe are in an ionized state. This is a correct observation, okay? The thing is, it is a correct observation until a redshift of order 8, give or take 2, at which redshift the stars turn out, okay? Which means at an earlier time, there were no stars, or not enough stars, to ionize the universe. Because if the universe had its own way, the cosmology has its own way, without stars forming, galaxies forming, and AGNs, etc., all kinds of complicated baryonic phenomena that happen at late time. So without stars around, actually, the universe would like to be in an almost entirely neutral state for these electrons. So it's only a relatively recent phenomena that stars started burning and caused this ionization. By the way, the details of this ionization are unknown theoretically. We don't know exactly what it is that gives the main force of ionizing UV photons to cause this rise in the ionization flow. Okay? But it happens. So our calculation, our earlier calculation of the optical depth of photon has to be modified, because in our earlier calculation, I just integrated, ignoring this change in the electron number density. So also, my scaling estimate of the QED rate is not correct, because it's a scaling estimate based on just redshifting the current free electron function. Okay, so this estimate is actually broken, right? Because NE, remember that the free electron function is NB times XE, as I defined it. And our XE is 10 to the minus 4 smaller than what we thought. So the QED rate goes up, as we said, but then very early on, at redshift of order 8, this poor thing drops back to nothing almost, by 4 orders of magnitude, and stays down. Okay? And then it starts to climb, but we don't care. So we have to modify this calculation, and now we have all the tools. Okay, here there is no problem. Now we have all the tools, and we can do this calculation. So what is the optical depth? And this I'm going to need shortly, so I should better not erase. So what is the optical depth now? A correct calculation of the optical depth, the number of scatterings that a CMB photon has from some emission time until today. Okay, now we have all the tools to really do it. Okay, and so let's write it as tau of Z, and by that I mean my photon is assumed to have been emitted at some redshift slice Z, and I calculate how many collisions it had until it gets to me. Okay? So this is an integral dt, as we said before, times NE sigma Thomson C, as we said before. Now NE is a function of Z, okay? And my integral goes from T naught to some T of Z. Now you know how to do these integrals. So that's an integral from 0 to Z, 1 plus Z, Hubble of Z, sigma Thomson C, and B of Z, X, E of Z. Okay? So, well, I set it up here. I'll continue over there. So my tau of z, we can pull out some factors, okay? So we can pull out in particular C sigma Thomson, the baryon density today, and the Hubble rate today, okay? And all the rest in the integral is dimensionless. So the rest of the integral is dz over 1 plus z square root. I could add radiation, but I won't bother to do it, and you can check that it's not important. And in here, I have 1 plus z cubed for the redshifting of just the total baryon density. And I also have xe of z, for which we have the answer, okay? And this would be the Saha equilibrium answer. It would continue to drop down, but this is the correct answer that I'm telling you. And it's not extremely important at this point. These numbers we already calculated. Okay? These numbers, this product of numbers is of order 10 to the minus 3, because it's just the current Thomson scattering rate over the age of the universe today. Okay, so this we have already done. This combination is of order 10 to the minus 3. And the calculation that we did before, although we didn't know how to write it like this, was assuming that xc is just 1 all along in redshift. If xc was 1, okay, then this integral, we also know that we have to go to somewhat high redshift, so the cosmological constant is not important. And so this scales like, let's call it tau naught, which is much, much smaller than 1. So it scales like my tau naught times an integral from 0. I can take just the matter density of here. So this is z squared in here and z to the 3/2. So I have z to the half. To the half xe of z. Okay? So if I'm allowed to continue my integration back to when xc becomes of order unity, then I can immediately estimate this integral. So in this region where xc of order unity, I can compute this integral, the contribution from z above this recombination redshift that we found. And this integral would scale like z to the 3/2, because it's integral dz times 1 plus z to the half. So the answer is z to the 3/2. And this redshift is of order 1,000. So 1,000 to the 3/2 is about 10 to the 3. So right at the time, well, it's actually a little more than this. So the actual number at 1,000 is a little more. I would find about 10 to the 3 at a few hundred. That's another one correction to what I'm saying. But it's clear that immediately when I cross the 1,000 in redshift and xc becomes of order 1, this number on the right becomes 10 to the 3 immediately, and then much larger than 10 to the 3, blowing up like redshift to the 3/2. So in here, there is a huge contribution to the optical depth. And the photons scatter many times in this region. The second thing that is clear, that we really had to go to redshift of order a few hundreds to get a contribution of order 1 for the entire thing. Yes, because this tau was 10 to the minus 3. We had to go to order 1,000 in redshift. My numbers are all wrong. Let me write them carefully. Right, because I have 1,000 to the 3/2 times 10 to the minus 3. This brings back my hundreds. So when xc is of order 1, I have here 1 plus z to the 3/2, which is roughly 10 to the minus 3, z over z recombination to the 3/2 times 10 to the 3 to the 3/2. So that's 4.5, right? Good. That's much better. So that's much, much larger than 1. Okay? So in fact, we hit the point at x equal 1. We hit the point of unit optical depth. at a redshift of hundreds, not of thousands. We would immediately hit it once we ionize. Okay? And that's what I wanted to say. Good. But then, this jump, we have an exponentially fast jump in the solution of the psi equation xe, and we fall down to an xe of 10 to the minus 4. Okay? So immediately when this happens, actually this xe becomes like a step function. It becomes extremely small, and there is no more contribution to the integral, and I can continue my propagation without ever scattering again. Okay? So this is why we have a last scattering surface. All the photons that we are seeing, almost all the photons that we are seeing are last scattering here around this transition. Just across it, we have a huge optical depth, many scatterings. Just after it, we have a tiny number of optical depths. And it's just this integral that you can compute immediately. So now what I want to do, I want to use this simple tool and just explain to you, and this is something that I don't think exists in any book or maybe any paper. And so I would like to explain this result to you. It's a relatively recent result. And what you see in this plot, it connects to Javier's lectures. I don't know if he will show it or not, but I will just satisfy myself in deriving it. So this plot is the constraint, the recent constraint from the Planck collaboration, measure Symbian isotropies. And they're putting a constraint in this plot on the annihilation of massive dark matter particles. Okay? So if indeed we have dark matter particles, and they are non-relativistic particles, and then they would be annihilating today as they have been annihilating in the early universe. Okay? And their annihilation, so what I'm saying here, let's imagine, and what they are saying here, they're saying, let's imagine dark matter particles, let's call them chi, massive. So m chi is the mass of these dark matter particles that we're thinking about. And you see it's in the ballpark of GeV and more. That's where the constraint is valid. So they're very massive. Okay? And they're annihilating, and they're assumed to be annihilating with this cross-section, sigma v. So with the velocity-weighted cross-section, sigma v. And they write brackets here, meaning that what we really want is the average cross-section. And by average, I mean it's a cross-section average over the distribution of initial states for the collision. So I have some distribution function of these chi particles, and I need to calculate the average cross-section for the annihilation. Okay? So that we're imagining that they're colliding with each other. Chi collides with chi through some interactions. We don't really care what interactions. And in this annihilation, they produce standard model final states. And one thing that I really like about this analysis is that we are not very sensitive to what is exactly the standard model final state. So I personally suffer when there is discussion on detailed model building for dark matter because we simply don't know what dark matter is, right? So any specific model is probably a complete shot in the dark. But when it becomes observationally interesting to me, is when you have a rather generic case. You have an analysis, an observational analysis, that affects a large class of such ideas, a generic class of such ideas, not some specific model. Okay? And this is what is happening here, because almost whatever these standard model particles are, what we are imagining here, that these annihilations are happening all the time. They should be happening all the time. We'll compute the rate. And in particular, they are happening in this early universe. So finally, I'm almost justifying the name of my lectures. So these annihilations are happening all the time, also in the early universe, maybe also today. Two chi's meet and give us a standard model shower of particles. Okay? And they're also happening here at this time. Okay? And now, when you inject a shower of particles into a gas of protons and hydrogens and electrons, then this shower is going to propagate. It will be really some hadronic or electromagnetic shower, or probably a mix of both. it will propagate in the gas. And as it propagates, this shower of standard model particles is going to hit hydrogen atom and ionize them. Okay? And the thing is that almost doesn't matter what this standard model final state is. It could be, say, protons and antiprotons coming from quarks and antiquarks, yes? Or it could be pions, also from hadronic decay. So this would be coming from quarks and from gluons in the final state. Or it could be plus and minus, or muons, etc. Okay? So for a large variety of standard model final states, these final states are going to produce a shower that will inject energy into the standard model plasma and ionize some of it. Okay? Now, the rate at which these collisions are happening, so I'll define this quantity shortly, the rate per unit volume at which these collisions are happening is the dark matter density squared times this velocity-weighted annihilation cross-section. Okay, so just n sigma v is what we looked at before. It's just the rate per particle for the interactions. So n squared is the rate density. It's in units of 1/second, 1/centimeter cubed. That's the rate at which these collisions are happening. Each of these collisions is providing a total energy of twice the chi mass into the plasma. Okay, so that's the rate of energy injection into this plasma. Now, what we are going to care about is how these annihilations are affecting the ionization history of the universe, because that's what the CMB experiments like Planck are so sensitive to. So we want to ask how much of this energy actually goes to ionize the plasma. And this does depend a little bit on the standard model final state, but not by a huge amount. So we'll use two factors to express this efficiency of ionization from this annihilation. So first, I'll write some number f, and I will say that of the energy that is injected to the standard model per each collision of dark matter particles, a factor f smaller than 1 is actually absorbed by the plasma. The rest of the energy can just escape, meaning if in this cascade there are some neutrinos, if I will go to quarks, the quarks will hadronize. They will go to, for instance, pions. Some of the pions will decay to muons and, for instance, muons and mu neutrinos. Neutrinos just go through. They don't do anything ever. The muons will decay and undergo an electromagnetic cascade and excite the plasma. Okay, but some fraction will escape inevitably. Okay, so this is the fraction of the energy smaller than 1 that is actually absorbed by the plasma. And second, what I really am going to care about is ionization, because what this effect is going to do, it's going to change the optical depth for photons to scatter since the last scattering surface, because it was going to change the ionization fraction. So what I want to care about is ionization. So I'll introduce another factor, and I'll say that I'll estimate that the factor of 1 minus xc/3 of this total energy, f of it is absorbed in the plasma, and a factor of 1 minus xc/3 goes to ionization. The rest of this energy can do whatever it wants. In particular, it can heat the plasma or lead to atomic excitations, etc. But roughly, this fraction will go to ionize the plasma. So the precise form of this efficiency factor can, in principle, be computed for a standard model plasma given the initial state. Okay? But this is a rough approximation that's good enough for us. So it won't be exactly this, but this is a rough approximation good enough for us. When this xe is much, much smaller than 1, this approximation suggests that about a third of the total absorbed energy actually ionizes hydrogen. Okay? And second thing we want, so now what we have with all these efficiency factors, we have total energy injection rate. But what we want is total ionization rate, okay, per unit volume. And for this, let me say that all of the energy that goes to ionization actually ionizes a hydrogen atom. So the number of atoms I'm allowed to ionize is the total energy divided by EH. Yes?
How exactly are F and 1 minus X equal to different?
Sorry?
How exactly are F and 1 minus X equal to different? What you talk about ionization?
How does it what? How do they differ? How are they different? This is a definition of some efficiency estimate, okay? And I gave you the words for it, but you can interpret it whichever you want. So I said, imagine you have a cascade in the plasma. Part of the cascade is just going to escape without interacting ever with the standard model. So in other words, if my WIMP dark matter is annihilating at redshift of 1,000 or at redshift of 100 and is going to neutrinos, neutrinos are just going to escape through the plasma as if it was nothing. You can compute the optical depth, you will find nothing, okay? So this was F. F was saying some of the energy is going to just go unfelt. And the 1 minus Xe is a rough estimate for how much of the energy that is absorbed goes to ionization. You can roughly understand it. So when Xe is equal to 1, the plasma is ionized. When the plasma is ionized, it doesn't matter what you inject into it. You cannot ionize it anymore, okay? So the energy would go to something else. Good. So it's a rough efficiency estimate, okay? And so now what I have, this thing is in units of ionizations of hydrogen ionization, per unit time, per unit volume. So when I write a continuity equation for the free electron function, okay, my evolution equation for the free electron function, we have one trivial term from expansion, as you know. This term is not particularly important for us. And then on the right, there is a collision term. There are processes that are changing the number density of electrons per unit time and in a comoving volume. So even if you froze expansion, some processes like this would change the number of free electrons. In particular, this process would increase the number of free electrons because it would take hydrogen and ionize it. So I can add this Q on the right-hand side. It's a positive source term for free electrons. These things are all the time exciting free electrons. Now there are other terms here on the right. There are standard model terms, okay? So standard model term, there is some ionization. Let's call it standard model. It's ionization by just standard model photons. Ionization and recombination, which is a very interesting calculation that we're not going to enter into now, and which the most important thing to point out is that in this critical time of the universe, just after this crossing of the psi equilibrium condition, all of these standard model processes are actually frozen out. They are very, very slow, okay? So they are not particularly important for us. I would actually ignore them, okay? And now this source term is going to affect how my free electron function behave in this regime in a very simple way. So I could write an equation, continuity equation for Xe defined over there instead of Ne. And neglecting standard model, this continuity equation just says this Xe dot defined as Ne over Nb dot, okay? The Hubble term drops off because the Hubble expansion affects the same way electrons and the total baryon number. So this Xe dot is Q over Nb, just the total baryon density, okay? And I have this term Q. So I have this equation that tells me how the fractional ionization function is modified. Now, because recombination is unimportant, and this is just a process that leads to ionization, recombination is unimportant at late times. It is important at early times, but we will just make a rough estimate of the effect. Then I can integrate in time to find what is the correction of Xe because of this term, okay? So actually, to be more precise, let me call this term delta Xe dot. By the delta, I mean this is the contribution really of the new physics of this dark matter annihilation to the Xe. Okay, let me erase the Saha equation. So that's very good. So we understand one of the effects that dark matter annihilation would have on the plasma. It will kick up, ionize some electrons. Now, this Planck experiment is extremely sensitive to, and it measures the detailed ionization history of the universe, especially around this region, but also a little later, okay? So it measured very carefully, very precisely this transition from fully ionized to non-ionized universe, because the last scattering surface is concentrated with roughly 10% resolution in redshift around this exponentially fast transition of Xe. Okay, so CMB experiments are very sensitive to that. And the CMB experiments are also sensitive to the little residual optical depth that we get by this step. Okay, this late reionization contribution to Xe. And so I can calculate some quantity, let me call it tau ionization, which is just defined to be the optical depth from z equals 0 to z equals z ionization. Okay, so over this interval, let me make an auxiliary integral calculating this quantity that is called tau ionization. This quantity will have a small effect. So what this quantity will do, we have some picture of photons coming from the CMB last scattering surface. And a small number of them is going to hit free electrons later on at redshift below about 8. Okay, we already know it's a small number because we estimated this integral. And they will distort a little bit the image, the CMB image. Okay, I'm happy to explain more detail later if you want. But it is a measurable quantity, what excess optical depth I get after the main thing, this main recombination event. Okay, so this tau ionization is observed by Planck to be of order 0.07 plus minus 0.02 or so. So it's a small number, as we know it should. We can easily compute it with an Xe of 1 with a step function of Xe all the way up to around z ionization. You'll get this number. It's of order 0.1, yeah? This is the number. This is measured by Planck. And what you should really take from this, since we don't understand in details the physics of reionization, this is really a measurement of the physics of reionization. What you should take for our exercise is that theoretically we have quite a lot of freedom to change this around. The theoretical parameters are not well understood. But what we don't have a lot of freedom to do, we don't have a lot of freedom to add optical depth beyond about this quantity, about 0.1 or a little less, to the photons after they have last scattered. Okay? This we cannot do. It will distort the Planck images. So we can estimate our dark matter annihilation effect by just calculating, doing a very naive analysis, no need for sophisticated softwares, etc., of what is the excess optical depth caused by these annihilations that are ionizing the plasma. What is the little excess optical depth coming from this ionization? So what will these ionizations do? These annihilations will take the standard model calculation of the free electron fraction, and we know they have to raise it a bit in some way. As long as the effect is small quantitatively, all they will do is distort the standard model calculation by a bit. So at z of 1100, they can do nothing because Xe is almost 1. And so we really have no room to ionize. So very roughly, we have like a step function for the effect on ionization of these annihilation events. But later on, they will work, and they will add a little bit of free electrons. So let's compute it. We have everything we need. Okay, so let us compute delta tau, the excess optical depth from a dark matter annihilation from today and until the point that this efficiency factor kills us. Okay, so this is just the usual time integral that we did before. So I can already factor out some things. So it's C sigma Thomson. Well, this I don't want to factor, actually. Let me keep it. So Hubble of Z from 0 roughly to Z recombination, because if you don't mind, let me replace this for simplicity by a step function of z rec minus z over 3, just to make our life easy. It's almost a step function because xe rises exponentially at that point over there at recombination. So I have my C sigma Thomson. And now I want to calculate the delta NE, only the excess little excess in free electrons coming from dark matter annihilation. And so my delta NE, I can write it as NB of Z times delta XE of Z. And I can get my delta XE simply by integrating this equation. Okay, so let's just do this integral. So write this again. And here I have another integral. And now please understand what we're doing. We're calculating the excess optical depth from 0 until some redshift Z. And what we want at this point in Z, we want this little excess of electrons. And causally, this little excess of electron is produced by integrating the effect of annihilation from the time where we're measuring up to recombination, okay? So this integral actually goes from Z to Z recombination. Let's go to Z recombination 2, okay? Right? It's also just a time integral of this. Q over NB. So we can just write it. So it's in time integral of, so let me replace here. Let me note that N chi is rho chi over M chi, because these are non-relativistic particles. Okay? So this I can write as rho chi squared over M chi squared. 1 power of M chi cancels off. Okay, didn't do anything. But I can write this term here. So I have rho chi squared sigma V 2 over 3 EH F and my step function. So I've already used my step function by cutting this integral at Z recombination. Okay, so if I pull all the factors out, the parametric dependence is immediately obvious. So if we have S-wave annihilating massive particles, then the velocity-weighted annihilation cross-section is just a constant, okay? So this is one of the numbers that I can pull out. And what I have sigma V F over M chi times a bunch of standard model stuff that you know, which is 2/3 Z equals 0 H naught squared. Okay, so actually I forgot, of course you should have corrected me. This is NB of chi because I had this NB in here. So this guy is actually down. The normalization cancels, okay? But I do have dark matter density. So I have rho C, let's call it, or rho chi at Z equals 0 squared, Hubble knot squared. Okay, all of this is good. And just a redshift integral. Now this redshift integral is dominated by high redshift. I can drop all the ones, okay? So I go from Z rec to 0, and this thing is 1 plus Z cubed. So I have, this is Z squared, and this is Z rec is still in matter domination. So here I have the Z to the 3/2, okay? So I have overall Z to the half, and I'm in matter-dominated region, so I have an omega m, because each of these Hubbles is proportional to square root omega m times 1 plus Z to the 3/2. So this is one integral, and the second one is from Z to Z rec again, times this, and that's it. we are done. Because when you plug the numbers in this result, what you find so all of this you know. This is a completely trivial integral. It scales like z to the half, z, so this together is z. It scales like z recombination cubed. So all this integral is about 1,000 cubed, okay? It's trivial to do with a coefficient of 2/9. All of these numbers we know from the locally or the currently inferred dark matter mass density. This is a model-dependent quantity just from cosmology, okay? And all of these are just cosmological parameters you know and the hydrogen recombination function. And what you find is a delta tau, which look roughly like sigma v times f over 3 times 10 to the minus 26 centimeter cubed per second, a number that many of you know, and the others will probably know tomorrow, times m chi over 10 GeV to the minus 1. And all of this combination, dimensionless combination of parameters is about 0.1. And this you should check in the quiet of your room. Okay? And that is the plot over there. So what the plot over there says is that, you see, all the region above the blue, all this blue region, above this blue line, is excluded by Planck. It excludes at a given m chi, this region excludes that coefficient, the velocity-weighted annihilation cross-section multiplied by f. This is our f over here, okay? So this is the excluded region, and the line is a line of constant sigma vf over m chi. This is why it's a straight line in log space. And this line cuts at a mass of about 10 GeV. This line cuts the value of, so really for f equal 1, this line would cut at 10 GeV. So actually a little bit, let me think about it. So it cuts somewhere here at a few tens of GeV. With f equal 1, it cuts, you know, about 2 10 to the minus 26, which is the number that I wrote there. I wrote 3 10 to the minus 26. So to a factor of 2 or 3. This line basically intersects a mass of order 10 GeV at this nominal 3 10 to the minus 26 centimeter cube per second WIMP cross-section. Okay, so that's f equal 1. This band that they write here is a very rough estimate that they're making for the possible values of this efficiency factor f given different initial standard model, different standard model final state for this annihilation. Okay, so f could be anywhere between 1 if what I annihilate to is an electron-positron shower, or it can be smaller than 1 for, say, photons or pions, okay? So this is a theoretical estimate of theoretical uncertainty on f. And this curve here of constant sigma v over f is just the curve that I wrote for f in the region from point few to 1, okay? So we understand where this line cuts the thermal relic region, it's around here. It's exactly the answer that we find. And the effect that are constraining is that this late-time dark matter annihilation are ionizing some hydrogen, as we wrote, and distorting the recombination history, adding some relic optical depth. We can get it quantitatively to a factor of few without running any software and understand the way this thing works. Okay, so I think this was a bit of physics of the early universe with a very recent result. And I hope you understand how this works. And I think I'll stop at this point.